Hello everyone. This video is being made as part of the deep learning course. So let's start with our topic, deep learning for anomaly detection in time series data. Throughout history, humans have been driven by the pursuit of predicting the future to facilitate development. This drive has led to the continuous collection and measurement of natural signals like temperature, wind speed, rainfall, etc. Additionally, in various industrial sectors such as business, finance, biomedical, and manufacturing, extensive data generation has become common, with data owners actively utilizing these datasets to enhance their products and services. Time series data, a prominent data type, has long been the subject of study with a key emphasis on unraveling patterns, trends, and underlying structures within chronological data for predictive purposes. This field encompasses various analytical techniques, including classification, clustering, forecasting, and anomaly detection, all aimed at harnessing insights from time-ordered data to anticipate future events and trends. What is anomaly detection? Anomaly detection is a crucial data analysis technique for identifying deviations from expected patterns or data points within a dataset. While classical methods like linear model based, distance based, density based supported machines are effective, they encounter limitations as systems become more complex. This challenge is especially pronounced in time series data, where considering both causation and the chronological order of observations along the time axis is essential for accurate anomaly detection.
Now we'll take a look at a background which is needed to understand time series analysis. First, we'll define what an anomaly is. According to Hawkins, anomaly is an observation that deviates so much from other observations that it allows a suspicion that it was generated by a different mechanism. With respect to time series data, it's a data point at a timestamp that shows unexpected behavior that differs significantly from previous timestamps. And the different types of time series anomalies are point anomaly, context anomaly, collector, minor, missing square, and drift, which is evident from the picture. So first, what's the point anomaly? It's a single data point that sharply or abruptly deviates from what's considered as a normal behavior based on historical data. It's like an outlier in the data. Such anomalies may appear to be temporal noise. Detecting these points typically involves setting an upper and lower data control limits known as UCL and LCL. These limits are boundaries which we define based on historical data. They represent the range of values under which these points appear under normal circumstances. So when a point lies outside of these boundaries, then it might be an anomaly. Next is context anomaly. Unlike traditional point anomalies, these data points don't abruptly deviate from what's considered as a normal behavior. Detecting these anomalies is challenging because they don't conform to typical upper and lower limits we set. They require understanding the context within which the data points occur. For example, in summer, we come across a short period where the temperature unexpectedly drops a bit. Individually, these temperatures may not be far from the usual range, but when we consider the context of the heat wave, then they stand out as anomalies. The next anomaly is a collective anomaly, which are a group of data points that individually may seem quite ordinary, but when considered collectively and examined over a longer period, will take a gradual shift in the behavior. These anomalies can be detected by considering long-term context and trends. We need to analyze the data over an extended time frame and spot the subtle shifts in behavior. Now we'll take a look at anomalies in multivariate time series data. Uh, these add complexity because we not only consider how data changes over time, but also different variables which relate to each other. As we include more variables, the patterns become more complex. So how to detect these anomalies? To detect these, we employ strategies like dimensionality reduction, which is a technique which simplifies the data by focusing on the most critical variables and reducing noise and complexity. Now we'll take a look at a few properties of time series data. The first property is temporality. Time series data is unique because it's a collection of observations that are ordered by time. There's a temporal correlation between each consecutive observation. This means that each data point in the series is captured at equal intervals and it depends on the past values as well. Mathematically, the joint distribution of sequence of observation using chain product rule is given as shown in this. Now we'll discuss about dimensionality. Dimensionality refers to the number of individual data points or attributes that are captured in each observation within a time series. There are two kinds of dimensionality. One is a univariate and other is a multivariate. In univariate time series data, each observation consists of a single real value data point measured at a time t. It's a sequence of single valued observation, like it's like tracking only a temperature in a day, like only a single parameter. Multivariate time series data involves ordered sets of multi-dimensional vectors. It is like a group of univariate time series data streams, and each represents the state of target system from different variables. For example, if you measure temperature, humidity, and wind speed simultaneously, then it's a multivariate time series data. And another property is non-stationarity. Non-stationarity refers to the property of time series where statistical characteristics are changed over time. And this is the equation which represents how are stationary conditions. And non-stationary poses a challenge for anomaly detection because data points appear anomalous at certain timestamps may not be actually truly anomalous when viewed in the context of changing statistical properties. And here are a few time series which are non-stationary due to reasons of seasonality, concept risk, and change points. Seasonality refers to recurrent and periodic patterns which are caused by various factors. For example, an online sales can spike during events like a Black Friday and then drop again. And another factor is the concept drift, which is a phenomenon where underlying statistical distribution changes over time. and this can be due to changes in environment or predictions. For example, customer preferences in a store might change gradually over time, and this can have an effect on the sales patterns. Another reason is change point. In manufacturing industries, equipment's normal operating conditions can change for various reasons, and due to these operations might halt. Coming to the next property, which is noise. In signal processing, noise refers to unwanted or random variables that affect signals during capture, transmission, or conversion. Noise can arise from various sources like minor fluctuations or errors in data measurement. When dealing with anomaly detection, distinguishing between noise and genuine anomalies can be challenging. And to enhance the performance, it's essential to understand the nature of noise and also take steps to reduce it during pre-processing stage itself. And we can do this by filtering techniques, noise reduction algorithms, etc.
So let's start section 3, that is industrial applications. Various industries have increased their competitiveness by adapting to the changing environment using the latest digital technologies like cloud computing, big data, mobile devices, IoT, AI, etc. Anomaly detection in these crucial sectors like fault detection, leak detection, and cyber intrusion, etc. is a must in order for the industries to stay competitive. Smart manufacturing. The idea of smart factory conceptualizes a highly digitalized and connected combination of facilities and equipment that can improve productivity and quality through automation and self-optimization. In an automated manufacturing process, equipment conditions are most closely related to quality and productivity. So, in order to ensure this quality and productivity, smart manufacturing can be discussed in these three types, that is production equipment, infrastructure facilities, and logistic automation system. Deep learning models have shown great promise in detecting faults and abnormalities in the above mentioned three types. So, let's discuss these three types and the propose deep learning models to identify the faults in these. Starting off with production equipment, data-driven models and machine learning techniques are used to detect failures and faults. LSTM, that is long short-term memory-based autoencoders, consists of an encoder and a decoder part based on LSTM network, actually are a type of recurrent neural networks, RNN. Stacked autoencoders are used for early fault detection in CNC machines, used for shaping and machining materials using the vibration data. This vibration data is actually collected from the machines in the factories. Particularly for the fault detection and diagnosis in semiconductor industry, manufacturing convolutional neural networks, that is CNN model is used. Next, infrastructure facilities. To ensure the stability of pumps, chillers, and scrubbers, techniques like discrete wavelet transformation combined with LSTM-A and CNN are used. First of all, these pumps, chillers, and scrubbers are very essential to maintain the temperature and pressure in the factories. So, in order to find the anomalies in these things, we use models like LSTM-A and CNN combined. Deep learning based anomaly detection models have been proposed for heating, ventilating, and air conditioning systems. These are also called HVAC systems. Pre-trained CNN models like AlexNet and LSTM are used for fault detection in chemical processes. LSTM models have been modified for monitoring and detecting faults in wastewater treatment (WWT) processes. Next, we are going to discuss logistics automation systems. This talks about these autonomous guided vehicles like the one shown in the figure. Autonomous guided vehicles (AGV) transport product components within the facility, reducing human intervention. AGVs can be monitored using vehicle dynamics and monitoring route and rail conditions. Non-linear vehicle dynamics is estimated using the extended Kalman filter and neural networks to ensure better control and handling of AGVs. AGVs generally transport products through ceiling rails. Neural network based methods monitor the position of the upper and lower rail cables and cable holders. Next, let's talk about smart energy management. Stable supply and efficient consumption of energy are essential to cope with rapid climate changes and resource shortages. Thus, anomaly detection in energy supply and consumption processes has become increasingly important. In terms of supply, if a power outage occurs, it causes significant losses to the consumers. In contrast, if energy is unnecessarily consumed, higher prices are paid and energy is wasted. As illustrated in the figure, a large amount of data are collected and reported in the smart energy management systems. These provides all involved individuals the opportunity to better understand and predict consumption patterns. So let's discuss some headings under the smart energy management. 1. Electric power. Electric power plants generate complex multivariate time series data, and anomalies in these data must be detected. Convolutional LSTM, CNN, and attention layers collect metric data, assess the severity of problems, and finally identify the anomalies within power plants. Losses on the consumer side include irregular consumption patterns, unnecessary waste, and instances of theft. These losses should also be detected by the above mentioned models and are detected also, thereby promoting efficient consumption and reducing wastage from consumer side. Treated water. Water treatment facilities consist of numerous pipelines that are susceptible to physical attacks and cyber intrusions. Real-world datasets like SWAT and WADI are available for researchers to study vulnerabilities. Advanced techniques like generative adversarial network (GAN), temporal hierarchical one-class network (THOC) with RNN are proposed. Manufactured gas. Purification and refinement processes directly influence quality of petroleum products like crude oil, hard coal, and natural gas. A CNN model has been prepared by training it on the gas oil plant heating loop dataset. This is a dataset name, which contains data points including instances of cyber attacks on utility systems. Managing gas leakages while transportation is essential for cost reduction and environmental safety. For this, a CNN model was proposed that monitors flow noise inside the pipes. Now let's talk about cloud computing systems. In cloud computing, client data are stored and managed in remote data centers by a service provider. These providers are required to allocate appropriate resources to users in real time while storing sensitive information securely. As cloud services become more popular, intrusion detection has become crucial. Hence, providers now leverage logs and time series data to monitor the states of servers and networks to detect deviation from normal patterns. Hundreds of thousands of suspicious events are continuously detected by such monitoring systems every day. Therefore, time series anomaly detection on cloud system with subsequent diagnosis of the current state and tracing of the root causes is important to maintain high service availability. Talking about server machines, these are the servers that monitor and store your data. Server monitoring includes metrics like processor load, network usage, and memory status that are crucial for optimal performances. Omni Anomaly is a model that utilizes variational autoencoder (VAE) with gated recurrent units. Omni Anomaly combines the GRU's hidden state and a stochastic variable from previous step serving as encode. This undergoes a planar normalizing flow to learn complex distributions and is connected to the previous step via a linear Gaussian state space model for capturing temporal dependencies. Next, talking about network and framework. Monitoring of network systems and distributed processing frameworks, which together consider the network graphing, is essential. A trained autoencoder model with one encoder and two decoders is proposed to identify the network anomalies. A graph-based method has also been proposed to detect anomalies in big data processing frameworks. This approach correlates sensors using attention layers, captures temporal dependencies with GRU, and increases performance by jointly applying forecasting and reconstruction results.
Now we will discuss a few classical methods that were used to solve the problems of anomalies in time series before deep learning was popular and the challenges which were faced. First, we'll explain about time and frequency domain. Time domain analysis refers to examining how data values change over point by examining the trends anomalies based on predictions in time domain. And in frequency domain analysis, we consider Fourier theorem, which states that any periodic function, no matter how complex, can be expressed as a combination of periodic components like sum of sines, cosines, etc. In time series data analysis, discrete Fourier transform is a commonly used method for frequency domain analysis. It converts raw time series data into frequency spectrum. This equation shows how a frequency value is transformed from an input data xt, which belongs to time domain, and xk belongs to frequency domain. Now we'll discuss about statistical model. Like in general time series analysis, one approach is to create a statistical model to mathematically describe the data's characteristics. And statistical measures are mean, variance, median, quantile, kurtosis, and skewness. By calculating these measures and potentially others, we can create a model that is the typical behavior of time series data. Once we have this model, we can use it to inspect newly added time series data. By combining the characteristics of the new data and the old data, we can determine whether the new data points fall within expected range or if it's an anomaly. And the next model is a distance-based model, which relies on calculating explicit distance between two sequences and using a similarity metric to assess their similarity. One method is the Euclidean distance, which is defined as the length of segment between 2 points xi and yi, and this is the formula which calculates the Euclidean distance. And the another method is a time warping method that allows non-linear alignments between two sequences that may be locally out of phase, and we calculate the distance between these two. And this is the algorithm which defines the dynamic time warping. And the algorithm is that we create a cost matrix C using dynamic programming algorithm, and then we trace back from bottom right corner of this cost matrix to top left corner to find optimal warping path W, and we choose previous points with the lowest cumulative distance, and then we finally calculate the final distance using optimal warping at W, which is the final step. The next model is a predictive model. The predictive model which is used is ARIMA, which is a combination of AR, MA, and I. So firstly, AR is an autoregressive model that models a random variable x at timestamp t and is a weighted sum of the past values, and it is shown in this equation where phi I p is a correlation coefficients, and epsilon is a noise, and p is order of the model. And another is the MA, which is the moving average model, which computes the weighted sum of the lag prediction errors, and this is the formula of the moving average model. And I is the integrator, which represents the difference between the timestamps, consecutive timestamps. And this is the final ARIMA model equation, which is a combination of AR, MA, and I, and it is used to forecast future values. And here is mu is a constant, and YT is a difference between YT and YT minus 1 outputs when T is 1. And each value depends on previous observations and also the prediction errors. Now we'll discuss about a clustering model. So clustering model is divided into various mini steps, and the first one is mapping into multi-dimensional space, where a time series data is mapped into a space where each dimension represents a feature or attribute of the data. And the next is clustering algorithms, which are applied to group similar data points based on their proximity. And another is handling mixed attributes. Clustering algorithms may sometimes be insufficient when datasets have mixed attributes, for example, numerical and categorical values. And to address this, K-prototypes algorithm was introduced, which measures the dissimilarity between mixed attributes, considering the numeric and categorical attributes. And this is the equation which measures the dissimilarity, where x and y are two mixed data types, and this is how they are represented. And also it's efficient for large scale data, as it can be used to speed up techniques, and also parallel processing of data can also be done for faster processing among multiple machines. And we can also structurally cluster algorithms for networks are present, which is a density based clustering algorithm designed for graph data structures. This boosts efficiency without compromising clustering quality, even when there's millions and billions of edges. And an important method is MapReduce, which is a widely used parallel processing model, which we will be discussing later. And scalable k-means. Scalable k-means plus plus uses MapReduce during initialization phase, and this enhances the scalability of the model. Now we'll discuss some of the common challenges which we face. The first one is the lack of labels. This makes difficult obtaining label data, and also collecting label data is intensive both time and resource wise. And class imbalances are introduced between normal and abnormal data, which is hinderful to training. And another challenge is complexity of data, where monitoring individual univariate data is impractical as dimension increases. Like for example, in industrial processes, there may be a lot of dimensions, and it is impractical to measure all of this. And traditional methods struggle a lot with this. This causes the performance to drop a lot.
So now let's start section 5, that is deep learning for anomaly detection. Here we focus on recent anomaly detection models that have been used to overcome the challenging issues mentioned in the above section. Therefore, the following assumptions are made. That is, semi-supervised or unsupervised learning, that is, data is considered as normal for semi-supervised even though some contain the final state. Models should effectively understand and use the complex multivariate time series data. All the proposed deep learning models are analyzed from three key perspectives: how models define intercorrelation between variables, how they model temporal context information, how they establish anomaly scores or thresholds. Dimensional reduction is a method in which we can intercorrelate variables and find the intercorrelation between the variables. Here we do the stuff. Dimensional reduction reduces the complexity of the large scale systems by considering only those few significant factors required required so that it reduces the computation. This is done by using linear algebra methods like principal component analysis and singular decomposition combined, or neural network based methods like autoencoders and variation autoencoders combined. A drawback of this method is that it is difficult to pinpoint the cause of anomalies in the system. This is because as we are removing some factors like which are less significant, this leads to data loss. So we can't pinpoint the anomalies exactly. A second way to find the correlation between variables is a 2D matrix. A 2D matrix is a representation where it is easy to understand relationships and variations among multivariables in data. As 2D matrix considers a joint behavior, so this is most often used for identifying anomalies. Consider two different ways in which 2D matrix elements can be calculated, assuming matrix as empty. Now let's see these two equations through which we can calculate each and every element in the matrix. Now, what's the difference between these two equations? The first equation calculates the matrix elements by measuring the similarity between variables at the same time point. It does so by calculating the average product of the variable values with the time lag delta. Second equation calculates the matrix by considering the differences between variables at the same time point. The first equation is more sensitive to anomalies than the second one because the second equation focuses more on the differences rather than the correlations. A third way to find the intercorrelation between variables is the graph method. A directed graph is used to represent the relations between variables, with each edge signifying connection between two variables. Attention score, that is alpha ij, measures the influence of node j on node I. This is calculated as follows, using the formulas that I mentioned below, where Eij is the edge specific function that takes into account the feature vectors of node I and j. In general, the leaky ReLU function is used for this. Modeling temporal context. The history of a sequence contains a great deal of knowledge about its behavior and can suggest future shifts. Hence, estimating the distribution alone is limited in detecting context and collective anomalies. In time series applications, the temporal context should be considered when modeling the normal status. Models we are going to discuss under temporal context are recurrent neural networks, convolutional neural networks, hybrid models, and attention mechanisms. Recurrent neural networks. RNN majorly used to recognize pattern sequences and predict expected value, identifying anomalies by calibrating the difference between predicted and actual sequence. RNN has also been extended for variants like LSTM and GRU. LSTM and GRU try to learn long-term dependencies by studying only relevant previous states. These can also handle issues like vanishing or exploding gradient problems. Shown to the side is a dilated RNN to extract multi-scale features by using a skip connection between the hidden states. Shown is a 3-layer dilated RNN that extracts features from each layer, considering long and short-term dependencies. Convolutional neural networks. Even though RNN is the general selection for modeling time series data, CNN sometimes surprisingly gives better performance, and this occurs when the short-term data analysis, that is data analysis for only a short term, is done. CNN is generally used for image processing. CNN captures the intricate features in sequence by introducing non-linearity through pooling layers. However, CNN focuses on learning the patterns in time series data instead of explicitly capturing the temporal context. That is, it in fact learns the patterns and tries to predict the data using for assuming that it follows the same pattern, but that is not the case. You have to consider all the previous states, the order in which the previous states have appeared, and CNN does not do it. So in order to address this issue, another variant of CNN called the temporal convolutional networks (TCN) is introduced. TCN provides three distinct advantages, like TCN ensures that info from future doesn't influence the past, preventing data leakage. TCNs similar to RNN can handle sequences of varying length. TCNs can effectively analyze data over long periods by combining deep networks and dilated convolutions. Hybrid models. Hybrid models imply combining two specific models to get a new model. When monitoring time series data using a sliding window, the anomaly patterns will actually depend based on the window size. To solve this, a hybrid approach that combines spatial and temporal information simultaneously is proposed. This model is based on the idea that multiple windows of sensor data, each with its covariance matrix, organizes data that can easily consider both spatial and temporal aspects. A pioneering model called CONV-LSTM, convolutional LSTM, was introduced. This approach enables the model to learn state transitions with fewer parameters. In other variations, autoencoders and generative adversarial networks (GAN) are used, where convolutional LSTMs in the encoders capture spatio-temporal context from previous steps. Additionally, a temporal attention mechanism adjusts the contribution of previous feature maps to update the current one. Anomaly criteria. The above proposed models are designed to learn data by minimizing a specific objective or a loss function. Once the models are trained, they are applied to the system and machinery state diagnosis. In general, diagnostic results are expressed in numeric to help understand a given result are expressed in numeric to help understand a given status. We call this numeric indicator an anomaly score. The greater it is, the more likely the state is to be abnormal. Specifically, when the score exceeds a certain threshold, the corresponding data point is determined as an anomaly. In the past, domain experts decided this threshold empirically, but now it is decided according to the model training result. Some models employ an adaptive threshold that continuously adjusts to the changes in data over time. So now, earlier threshold used to be set manually, but nowadays we can we can change the threshold as per the data. These methods are categorized under three categories, that is reconstruction error, prediction error, and dissimilarity. So reconstruction error. Several models like autoencoder, variation autoencoder, GAN, etc. utilize reconstruction errors as anomaly scores. Reconstruction error is a metric used to quantify how accurately the model can reconstruct the input data. It measures difference between the original input data and the data generated or reconstructed by the model. AI-based models extract features from input data and attempts to reconstruct them. VAE-based models estimate data distributions and generate samples. GAN-based models explicitly create samples that closely resemble input data. These models might differ in their training methods and objectives, but they calculate anomaly scores in a similar manner. That is the difference. All the models aim to reconstruct data such that it resembles the input data, and then measure the difference between input and generated data to calculate the reconstruction error. Prediction error. There are two common approaches under this section to derive anomaly scores. First approach is to either assign a binary value 1 or 0 based on the probability of the data point to be classified as an anomaly or not, that is a normal or not. This method accesses whether the expected label matches the actual ground truth label or not. The second approach, that is the most used approach in this prediction error, is involving predictions, the expected value for future time steps. In this case, the prediction error is calculated as the difference between the expected value and the actual observation. The second approach is widely used as it doesn't rely on binary labels, which can be insufficient and challenging to define accurately. The third and the last one, dissimilarity. Dissimilarity-based methods in anomaly detection access how much a model's derived value differs from the distributional cluster of accumulated data. Various similarity metrics like Euclidean distance, Minkowski distance, cosine similarity, and Mahalanobis distance are used to measure dissimilarity. Models like THOC and TCN-GMM extract features from time series data using techniques like dilated RNN and TCN. These extracted features are grouped into clusters or have the distribution estimated using methods like deep support vector data description, that is support vector machines, or Gaussian mixture model, GMM. THOC measures similarity with cosine similarity, while TCN GMM employs the Mahalanobis distance as a similarity metric. Multistage TCN uses a multivariate Gaussian distribution to estimate the distribution of prediction errors and calculates the anomaly scores based on the Mahalanobis distance between the current prediction error and the pre-estimated error distribution.
Now we will discuss the guidelines for practitioners. So first we'll start with the detection strategies. First is the real-time detection strategies, which are beneficial because they can only detect the actual anomalies, and it's crucial for online banking, finance, etc. that has to respond quickly to these such incidents. And inference time varies based on computational complexity, resources, and with higher complexity taking higher time. CNN models process input data at once, and so results will be faster. When coming to early model, this anomaly, when it is incurred, when an anomaly incurs a severe damage, then early warning provides a warning earlier on about this. These methods are essential in scenarios where severe anomalies can result in severe damages. So preventive maintenance schemes in manufacturing aim to predict and prevent the breakdowns to reduce the maintenance cost. Key challenge is managing false alarm and missed anomalies detection. So a higher threshold suppresses false alarm but may miss real anomalies. And another strategy is a sliding window and incremental update. In sliding window, some models process historical data points using a fixed window size. The window size affects the length of temporal dependency detection. So practitioners should carefully select the window size based on dataset characteristics. Excessive sizes may sometimes overlook anomalies, and smaller sizes may fail to capture long-term dependencies. In incremental update, models update predictions for new data through marginal computations, and it's particularly useful in streaming environments where data arrives one by one. So it actually offers computational benefits, especially in scenarios with large data streams. So autoregressive models like GRU and LSTMs, they support incremental updates. Now we discuss about a few training and pre-processing techniques. So first is a loss function. Time series anomaly detection use various loss functions to model the normality of data. The first is adversarial loss, which is inspired by Goodfellow et al.'s work. Adversary formulations enhances the generator model capabilities. The discriminator assesses the generative component and also generate anomaly scores post-training part. So formulated as a two-player game, like this is the equation which shows how it is formulated as a two-player game, and the results can be remarkable, but it can be unstable and like mode collapsing challenges may also occur. Other one is reconstruction loss, where autoencoders are a favored choice for anomaly detection, assuming that they don't reconstruct normal data as well. Training loss involves reconstruction losses, ensuring that autoencoders capture normal data patterns, and this is a typical form of how A's are captured, where ST is an observed data point and ST is a reconstructed data point at a timestamp. Now we will discuss about prediction loss, which is enforces accurate prediction using past data or future relationships. Prediction-based approaches compare predictions with real observations. So similar to reconstruction loss, but there especially represented the reconstructed data back create and test a prediction for the real observation history. So it's applied during inference generally, and it's suitable for early warning systems. And another more important one is negative log likelihood, where we minimize the negative log likelihood to capture normality within the data set. And GMMs, which are Gaussian mixture models, incorporate LLM and LLM loss functions. And this is the equation which shows how they are incorporated. Now we'll learn about batch learning and online update, and also an extension known as continual learning. So in batch learning, deep learning typically assumes that stationary data distributions and models are trained using a large batch of data sampled from the same distribution as test data. It's problematic when the data cannot be recollected after each update, so it's not suitable for non-stationary data streams. And in online update, we generally mistake issues with non-stationary data which is not addressed in batch learning. We can fine-tune models with newly appended data, but we have to we don't have to retrain from the scratch. Some deep learning methods use it, not all, and they use it to adjust thresholds for binary decision making during updates. So an alternative to online update is continual learning, which faces the plasticity stability dilemma. Uh, Plasticity stability dilemma is that neural networks should be plastic to learn new tasks to stable to retain important features. So we find to use new tasks may sometimes lead to catastrophic forgetting. Another property which we should be discussing for continuous is denoising. So, as we discussed before, the noise is often induced by sensors and it can degrade anonymity detection. So, we use various techniques, and one of that is smoothing, which exponentially weighted moving average is a recursive smoothing filter which is used. So, it's effective, but it requires determining the appropriate level of denoising. Another one is transformation of the noise. So, as we have already discussed, that it has both time and frequency domains. So, like using transformations like fast Fourier transform and Wave transform, we decompose data into multiple to frequency characteristics. The difference between transformed and original data is considered to be the noise. Another method in estimating is and denoising is estimation. So generally Kalman filter is used, and it represents data in a state space model, and it applies probabilistic estimation. And another most important model is deep learning, which we've been discussing all along. Deep learning models can memorize noise through training data set, and is small relative to model capacity. So it makes it challenging to distinguish noise from anomalies.